This is lecture 9A on the evaluation of constants and on the classification of differential equations. You might have noted, for example, in the equation for harmonic motion that there were some constants. Okay, here was a solution for harmonic motion. There was A times a cosine. For the spring, there was K over M times T plus B times the sine of the square root of K over M times T. Here we have two constants, A and B. All right. When we find this functional form, there might be extra constants such as this hanging around. They will satisfy the differential equation, but we need to go further to be able to evaluate these coefficients, these constants. This is called the general solution. If you can find values for A and B, then you arrive at the particular solution. Okay, and there's two rather famous ways of doing it, although there are other methods. Let's say that you have an equation relating the function and its derivative, some derivatives, and you're given the values of them at t equals 0. So say you know x of 0 and dx by dt at 0. You can take these values and evaluate the constants. In this case, we had an A and a B. If we knew that at x equals 0, the value of x at t equals 0 was 10, and the value of the first derivative was 0, we could plug that information in and find that b equals 0 and a equals 10. This would be the particular solution. I'll write it here. So x of t would equal 10 times the cosine of the square root of k over m times t. This would be a particular solution. Okay. When you have the differential equation and the values at t equals 0, you call it an initial value problem. Okay, we can eliminate this here. Now this is classical method 1, and classical problem 2. You have the differential equation, and then instead of having all of the values at t equals 0, you might have the values at the edges of the region of interest. Say you were trying to find the heat distribution in a plate of some kind of material, and you knew the value right here. Say you knew the temperature at this end, we'll say at x1, will at this point be x1, and this is x2, and you know the temperature over here at x2, then you can use these values to evaluate the constants of the problem. Now, instead of having all the values at t equals 0 at the beginning of the problem, you now have the values at either end of the problem. This is called a boundary value problem. So what I'm giving you here is just some definitions. You'll come upon them later. You can have other combinations too, but these are the two classical ones. So you have a differential equation. See, it's some function of time, and you have the value of the function and its derivatives at t equals 0. That combination gives you an initial value problem. So you have another differential equation, and you have the value of the function at the edges of the problem, like at the edges of the plate where you're trying to find the temperature distribution. That combination is called a boundary value problem. Previously, I gave you the solution for the differential equation, and the idea was to take the appropriate derivatives, substitute them back into the equation, and see if you do indeed have an equality. Many times, instead of being presented with a solution, you have to find it. And there are methods, but the method of obtaining the solution depends on the particular classification of the differential equation. And here are some of the classifications that are important. Ordinary and partial. It could be an ordinary differential equation or a partial differential equation. It could be linear or nonlinear, autonomous, homogeneous, and non-homogeneous. So again, what I'm giving you here is just vocabulary. But the idea is that some of these The methods of solution depend on the type of differential equation. A method of solving a linear differential equation may not apply, for example, to a nonlinear differential equation. So when we look at the differential equation, we have to sort it out. Is it ordinary or partial? Is it linear or nonlinear? Is it autonomous? Is it homogeneous or non-homogeneous? Once we have its classification, we can then go use a method to find the solution. We did the same thing in algebra. When you looked at an equation, you had to decide, is it a linear equation? Is it a quadratic equation? Because if it's a linear equation, you use one method of solution. If it's a quadratic equation, you might use something else, such as factoring or completing the square or using the quadratic formula. Here we're going to classify the differential equations, and once they're classified, then we will find different methods of solution. Okay, we're going to start with ordinary versus partial. So an ordinary differential equation, there is only one independent variable. The ones that I showed you before for the catenary and for harmonic motion were ODEs, ordinary differential equations, because there was only one variable. For the harmonic motion, let me find the pin here. X was a function of t. There was only one independent variable, it was t. For the catenary, y was a function of x. There was only one independent variable, in this case x. Now in a partial differential equation, okay, this is a partial differential equation, there are more than one independent variables. So if you have the height of a projectile, it depends on distance and time from the launch site. Y is the height. It depends on the distance and depends on the time. There are your two independent variables. This is a partial differential equation. The wave equation depends on three spatial dimensions, x, y, and z, and on time, t. So this is another example of a PDE, or partial differential equation. The second derivative of u plus with respect to x, y, and z equal c squared times the second time derivative. Okay, this is from physics. So here's the difference. Ordinary differential equation, only one independent variable, like x or t. Partial differential equation, more than one independent variable. For this class, everything we really study, other than for this classification, will be the ODEs. We can now look at the order of the differential equation, whether it be partial or ordinary, and the order is the highest derivative in the equation. So for the wave equation, or for the harmonic motion, we had the second derivative equals minus k over m times x of t. Okay, the highest derivative was the second derivative, so it's a second order equation. If you had an equation, say dx by dt equals some alpha x of t, the highest derivative is the first derivative, therefore it's a first order equation. So order depends upon the derivative, the highest derivative in the equation. Here's a similar example here for an equation for a population of unlimited growth. P is the value of the population. It varies with time. It is an ordinary differential equation. The highest derivative is the first, so this is a first order ordinary differential equation. This is a second order ordinary differential equation right here. This is another first order ordinary differential equation. The wave equation was a second order partial differential equation. Now let's look at the term linear. In a linear differential equation, the function and its derivatives appear to the first power only. There can be higher order derivatives, but they are not squared or cubed, or the square root is not taken of them. So a linear differential equation may contain higher order derivatives, but none of the derivatives or the function itself can be squared, cubed, multiplied together, etc. The constants in the independent variable may be squared or cubed or whatever, but not the derivatives or the function itself. That's where we decide if it's linear or nonlinear. So in summary, the condition of linearity of the differential equation applies only to the function and its derivatives. These are examples of linear differential equations. This is linear because you have the first derivative. It is not squared, cubed, nothing's multiplying, the function isn't multiplying it, and here's the function. This is linear. Okay. This equation you have, and the second equation, this wave equation, you have second order derivatives, but they are not squared or cubed, or the square root is not taken of them. Here's another linear differential equation. You have a second derivative equals minus k over m times the function. These are linear. Now let's look at a nonlinear differential equation. You've seen it before. So look at the differential equation for the catenary. It's second order because the highest derivative, here's the highest derivative, it's the second derivative. But note what happens to the first derivative. The first derivative is squared, added to 1, and then the square root is taken of that quantity. So this is a nonlinear, ordinary differential equation. It's also second order, so we have all these qualifiers. So you can see the contrast here between linear and nonlinear. For example, skipping that bit for a minute, that topic there, if I had say the equation looked like this. This would be a linear equation because the second order derivative is not squared, cubed, or raised to any power. Here's the first derivative. It is not squared, cubed, or raised to any power or multiplied by any other function or derivative. This would be linear. But once we take the square root and square it, once we do these two things, then it's nonlinear. I can write all the letters for it. Okay? So I hope you can see that difference. That's an important difference. What is a linear differential equation and what is a nonlinear differential equation? Now let's look at the next topic, which is autonomous. An autonomous differential equation does not depend explicitly on the independent variable. So here is a differential equation. So we look through this, what do we know about it? There's only one dependent variable, and that's t. So this is only one dependent variable. Because of that, this is an ordinary differential equation. The highest derivative is the second derivative. So this is second order. We look through there, we see the second derivative here. It's not squared, cubed, multiplied by another function or derivative. The square root of it is not being taken. Also, the function here, y of t, is not squared, cubed, is not multiplied by any other derivative or any other value of the function. So it is a linear second order ordinary differential equation. Now, is it autonomous? If we look through here, the independent variable is t, and there is a t in this equation. So it is not autonomous. If we look at this equation right here, there's only one independent variable. It is x. But there is no x in this problem. The second derivative is being taken here, the first derivative here, but x does not appear explicitly, so this is autonomous. And we're getting to the end of this vocabulary lesson here, and now we're looking at homogeneous versus non-homogeneous linear differential equations. For a homogeneous linear differential equation, a homogeneous differential equation does not contain any terms without the function or the derivatives. So it can be written in this form. There's some function of x, could have x itself in it explicitly, times all these derivatives, the nth derivative, the n minus 1 derivative, etc., down to the first derivative to the function itself. But every single term has in it either the function, this one has a function, or these terms have the derivative. So you can write it in this form as equal to 0. If it's a non-homogeneous, again, linear differential equation, then there is some function of x here that is not multiplied by either the function or one of the derivatives, and it can be written in this form.